Imagine calculating the probability of finding an electron in a box, and the answer comes out as -20%. Not unlikely, not rare, negative. At that moment, the problem is no longer the electron. The problem is the language of probability itself. Quantum mechanics tells us to square the wave function. That is the Born rule. But why that rule? Why does nature translate possibility into probability in exactly this way? Maybe Einstein's question was incomplete. The deepest question is not whether God plays dice. It is where the dice table exists. For almost a century, physicists have used the Born rule with extraordinary success. A wave function evolves, a measurement is made, and the squared magnitude of that wave function gives the probabilities of possible outcomes. This rule works, but working is not the same as explaining. It is as if the universe gives us a probability table, and physics learns how to read it with perfect precision. But the table itself still raises a deeper question. Where was it printed? What decides that this is the correct language of probability? PTQ begins by changing the order of the question. It does not say that probability exists everywhere from the beginning. Instead, it asks, before probability can be physical, where must observation first become possible? In this view, the deeper structure is larger than the world we directly measure. It contains geometric information that is not automatically observable. So before we speak about probability, we must first speak about projection. Only after a physical projection selects an observable sector does the word probability begin to have a precise meaning. Not probability first, then the world. First, the observable world, then probability inside it. Imagine a vast, dark theatre. Behind the stage, there are props, cables, unfinished movements, and actors who never enter the light. Something is happening there. But from the audience, it is not yet a play. It has no stable scene, no measurable outcome, no probability table. The projection acts like a spotlight. Only the structures that enter the illuminated stage become part of the observable sector. Only there can we ask what may happen, and with what probability. In this framing, probability is not a property of the entire hidden backstage. It is a language spoken only on the lit stage. But a stage is still not enough. To define probability, we also need a ruler. In ordinary quantum mechanics, this ruler is the standard inner product. But after projection, the geometry of the physical sector may be distorted. A flat ruler cannot measure the true distance on a curved planet, and a naked eye cannot focus a distorted image. This is the role of the G metric. It is not decoration. It is the physical measuring rule that tells the theory how states should be compared after projection. Like a corrective lens, it does not invent the world. It allows the projected world to be measured consistently. The G metric cannot be chosen freely. It must fit the way the system evolves. In pseudo-Hermitian or PT symmetric frameworks, the Hamiltonian and the metric must be compatible. The engine and the measuring device must agree. If they do not, the theory may still produce numbers, but those numbers may no longer behave like physical probabilities. This is why the metric matters. It protects the probability language from breaking. It prevents the projected world from being measured with the wrong ruler. A wrong ruler may turn possibility into nonsense. A compatible ruler allows probability to remain physical. A valid probability rule must pass one simple test. Total probability cannot leak away. If all possible outcomes add up to 1 today, they cannot quietly become 0.8 tomorrow. In the PTQ picture, the same G metric that measures states also defines how probability flows. This produces a conserved current. A useful image is a sealed geometric channel filled with luminous fluid. The fluid may move, it may spread, it may interfere with itself, but none of it disappears. and none of it appears from nowhere. Probability becomes a conserved flow inside the projected sector. Now the pieces connect. Projection selects the observable stage. The G metric defines the physical ruler. The conserved current keeps probability from leaking away. And together, these conditions shape the G-born rule. In ordinary quantum mechanics, the ruler is already aligned. G behaves like the identity, so the generalized rule returns to the familiar Born rule, the squared magnitude of the wave function. This is the bridge. PTQ is not replacing the standard rule with a random new one. It is asking whether the standard rule may be a special case of a deeper projection-based grammar. A grammar where observation, measurement, and evolution must speak the same language. This does not solve every quantum mystery. It does not explain wave function collapse by itself. It does not prove that reality is projected, and it does not replace standard quantum mechanics. The claim is narrower. If physical reality is described as a projected, observable sector, then probability should not be defined before projection. It should be defined after the stage, the ruler, and the conservation law are in place. So perhaps the old question was incomplete. Does God play dice? Maybe. But the deeper question is, where is the dice table? Where is the observable sector in which the dice become real? And if probability only becomes meaningful after projection, then projection may leave something behind. A trace, a residue, a geometric fingerprint. Next time, we enter Palatini gravity and ask whether the mathematical background we thought could be erased might be the universe's own signature.